All right, so we are going to just take a look at applications of all of the stuff that we've learned so far in this unit. The application stuff should be relatively similar to the applications that we did in degrees last year. So the only difference here now is that we're using radians instead of degrees. Does anyone remember from grade 11 last year any of the applications that we did of trig functions? What are trig functions useful for representing? What types of things? Wonder how you came up with that one. What's that? Sound wave could be something, yep. Amplitude and frequency, yep. Pardon? Yeah, the motion of a clock. So anything that is periodic, so it returns to the same values over a set period. So a clock, for instance, keeps time. So the minute hand, for instance, if we were looking at tracking that, returns to the same location around the clock at the same, over the same time interval as it goes around. So anything that's periodic, really, that cycles around at the same rate, could be represented by a sine or a cosine function. Tides in an ocean, yes, because those are by the rotation of the moon. So pulling in and pulling out over the regular time interval. Anything else that you guys can think of? Hey, your heartbeat or your resting heart rate might be a good one. So beats per minute, that kind of idea. Over a regular time interval. Of course, that changes if your heart rate is elevated, like if you're running or something like that. Other thoughts? Carousels, we did a lot of those last year. Yeah, so we'll take a look at a couple of these. We just need to remember our transformation equation here, so I'm just going to write that up at the top. Okay, and of course we know this can be cosine as well. So sine or cosine for that one. Okay, so our first scenario is that we have a Ferris wheel that has a diameter of 15 meters. It's 6 meters above ground level at its lowest point. It takes the rider 30 seconds from their minimum height above the ground to reach a maximum height of the Ferris wheel. Model the vertical displacement of the rider versus time using a sine function, and sketch a graph of this function. Okay, sometimes it's actually more helpful to sketch first and then decide on the equation after. So I'm actually I'm going to start with the graph, and then we're going to add some labels onto that graph, and hopefully that graph will help us develop our equation. Okay, so this is height over time in seconds and meters. And the minimum height that my rider can be above the ground is 6 meters. What's the maximum height my rider could be above the ground? How high off the ground? 15 is the diameter of the Ferris wheel. 21, right? Because 6 meters off the ground and then another 15 would be 21. What would be the middle height of the rider above the ground? What's between 21 and exactly between 21 and 6? 13.5. Okay, where does my rider start as far as height? What does the question say? Where do they get on? Well, I think common sense tells us that they would get on at the bottom, although I would probably be a little bit more clear about that. But it does tell us that it takes 30 seconds from the minimum height to reach the maximum height. So I'm going to assume that this, why did this all of a sudden? Can't get rid of this. Oh, there we go. I'm going to assume that the rider is going to get on at the bottom of the Ferris wheel. That just kind of makes sense to me. So at a time of 0, they're at a minimum height of 6. Okay, and it said that it takes them 30 seconds to get up to the maximum height. That's up here. How long would it take them to get back down to the minimum height again? If it takes from the minimum height to the maximum height 30 seconds. Another 30 seconds, right? So at 60 seconds, they've done a full rotation. Where do these points come into play, those middle points in between? When does it hit?
Between 15 and 45.
Okay, so between 0 and 30, it must hit that middle value, and also between 30 and 45. So there's our rotation here. Oops. Okay, this is just a really basic sketch. It doesn't have to be amazing. Just looking for, in general, what this looks like. Okay, so this should help us to develop an equation from here. So let's talk about A, K, D, and C. So, can someone grab that back door there? So my amplitude. My amplitude is the distance from the midline to the max or midline to the min. Jonathan?
It'd be 15.
It would be 15. So in circular questions like this, it just so happens to, oh, actually, not 15, sorry.
13.5.
Not quite.
Oh, 7.5.
7.5. So in circular questions, it just so happens to be the radius of that circular object. However, if I'm not sure, this is my max and this is my min. How do we find A with max and min? What's the formula that we talked about? Yeah. So if I'm really not sure, by looking at my graph, I can do max minus min over 2. And that should give me my A value.
But you just do the midpoint minus min.
Yeah. So it's the distance from that middle point to the minimum. So you can do that too. You should get 7.5. Any ideas what our C value would be here?
That would be max plus min divided by 2.
Yep. Do we have the middle of the max and the min already though?
Yeah, we already did.
What's the middle?
13.
13.5. This is the midline, right? Okay. How do we find the K value?
360 divided by.
Not 360, we're not dealing with degrees. Okay, so 2 pi divided by the period. How long does it take the Ferris wheel rider to complete one full rotation? 60 seconds, right? So it's going to be 2 pi over 60, which will give us pi over 30 as our K value.
Wait, what is B again, sorry?
B is the period of the function, so the length of one full cycle. Okay, and this question asks us to find this as a sine function. So if I'm looking at a sine function, how do I find the D value of a sine function?
You look at the rising midpoint.
Okay, so where is the location of the rising midline? Sam?
It's at 15.
Right or left?
Right.
Perfect. So I'm going to look along this midline right here, and I'm going to find where it goes up into a rising midline as I trace my graph left to right. And that occurs at 15 units to the right. So we would say 15 right. And now we're just going to put this all into one equation here. So I'm going to use h at t for the name of my equation because it's height versus time. And our A value is 7.5. K is pi over 30. Our x here is being represented by t, so I'm going to use t instead of x in the bracket there. 15, right, should look like minus 15 in your equation. Oops. And our midline is up 13.5. And there's our equation. Fayek.
Would it be different? Because I thought the k-value changes like as it's like form, like when you just represent it like that, like when you equation. Did it change that or no?
Only when we're doing transformation. So if I were to now go and like do actual transformations of the sine function, then I would use the reciprocal. Yeah. Any questions on this one? Emmanuel.
Why is, so C is usually how much something goes up by, right? Like, right?
It's like the vertical displacement. So how much our graph has been like shifted up or shifted down.
Okay, so it would be the midline then.
Yeah.
Okay, cool.
So the midline of a regular sine function is usually at 0. And that will be like, it separates the mountains from the valleys. So this one has shifted up 13 units. Anything else, guys? Okay, let's try another one. Can I scroll?
Sure.
Okay. Mr. Ponson has the heating system at King's set to reach a maximum temperature of 76 degrees Fahrenheit and a minimum temperature of 66 degrees Fahrenheit. This cycle repeats every hour, starting with a maximum temperature at 6 a.m. Write a cosine function that gives the temperature at King's as a capital T in Fahrenheit as a function of t hours after midnight. Sketch a graph of the function.
I don't understand that.
Well, let's unpack it all. Okay, I'm going to start with a sketch here. So x here is time in hours after midnight. And y here is temperature in degrees Fahrenheit. Okay, I'm also going to do a little part of my graph that's squished here, just so that, because I'm not going any lower than 66, so I really don't need any values below that. So we're just going to start our graph at 66, and our graph will go up to 76. What's the middle temperature between 66 and 76?
Five?
5?
Oh,
71.
That would be 71.
71. If I wanted to find the middle of two numbers, how do I calculate that? Alexandra? Yeah, it's like finding the average of two things, right? So we'll add them and divide by 2. 5 was close, but just a little bit off. That's okay. So this just means we're compressing the bottom of this graph so that we don't have to like go all the way from 0 all the way up to 66. A little bit better. Okay. So in this case here, this is time in hours after midnight. So if I start at 0 here, I would consider 0 to be 12 a.m. And then I'll have like 1 a.m. I'm going to space this out a little bit here, so we might actually need to extend our graph a bit over here. I might even just take up this whole space here. So that we can get to 6 a.m. Maybe I went a little too far with that. Sorry. 3, 4, 5. There we go. That's good. So this is 1, 2, 3, 4, 5, and 6 right here. Now I went up to 6 because it tells me information about 6 a.m. So it basically just tells us that at, 6 a.m., yeah, we're at a maximum. So I know that at 6 a.m. we're up here. How long is a cycle here? Like how long would it take to reach from max to max?
Every hour.
Every hour. So does that mean every hour we're at a maximum temperature? If it's one full cycle, a cycle can be measured max to max, right? Or it could be min to min or midline to midline with a mountain and a valley. So every hour on the hour, because the cycle is an hour long, I'm going to reach a max temperature. So at 12 a.m., okay, and of course, maybe the cycle changes at night. Maybe they keep it a little bit lower at night. But I would assume if this continues to run every hour on the hour, I will be hitting a maximum temperature. When do I hit the minimum temperature then? At the beginning of the hour, I'm hitting a max. Like every hour on the hour. 12 a.m., 1 a.m., 2 a.m. Jonathan?
Every time the minute timer strikes 30.
Every half hour, I hit a minimum, right? The minimum happens exactly between the max and the min. So if at 12 a.m. and 1 a.m. I'm at maximums, I must be at the minimum halfway between that, which is like 12:30, 1:30, 2:30, and so on, right? So if we look at our graph here,
Yeah, I thought it was 71.
so halfway between those two things, I'll be at 71. But halfway between max and max is a minimum. So I'll be hitting 66. I apologize for my bad locations here. You get the point. Okay, so that will be happening at like every half hour. And then when do we hit the middle temperature of 71 degrees? 45 minutes, and also there's another one. So 45 minutes, it would hit the middle, and 15 minutes. So every 15 minutes and 45 minutes of the hour, we'll hit those middle temperatures there. All right, so we've just graphed quite a few cycles here. Okay, so there's my graph of my function. I think we have a midline here. You don't have to draw it all the way down, but I think our C is 71 degrees. What would my A be here? What's the amplitude, distance from the middle to the max or middle to the min? Liam? 5 degrees, or we'll just put it as 5. K value? Can anyone help us with that?
So it would be 2 pi over 1, so this is 2 pi.
Yep. So this is 2 pi over, the period is 1 hour. It takes 1 hour to complete a cycle, the question told us. So K must be 2 pi. And the D value. So this asks us about a cosine function.
D equals 0.
So we could say 0. We could say 1 to the right, 2 to the right, 3 to the right, 4 to the right, 5 to the right, 6 to the right, right? There's infinite maximums that we could say here. Now this technically tells us that our cycle starts at 6 a.m. So just using my common sense here, potentially maybe the cycle doesn't happen when people aren't in the school. So we could say maybe just to be certain about the question telling us it starts at 6 a.m., we could say 6 units to the right, just to indicate that the cycle technically starts at 6 a.m. So I might actually just put 6, right? But if you said 0 here, that would be fine. I would have to give you a little bit more indication as to whether that cycle repeats overnight or not. Okay, so let's put together our equation then. Maybe I'll call this F at T, F for Fahrenheit, lowercase t for time, just so we don't have two T's in here. And there's our function. Yeah. So the d value for cosine is the location of the nearest midline, because a regular cosine function starts at a maximum at 0, 0. Or not 0, 0, but when x equals 0. So I look for where the maximum has moved as far as left and right to determine the d value of cosine. For the d value of sine, a sine function starts at a rising midline. So it goes up into a mountain from the point 0, 0. So if I look along my midline here for a rising midline, if I were looking for sine for this one, I could say 0.75 to the right for that one, because it's rising up into a mountain from the midline there. So cosine, looking for the nearest max to the y-axis usually. In this case, we use 6 to the right because it told us the cycle started at 6 a.m. And then for sine, we're looking for the rising midline, closest rising midline to the y-axis.
Wait, so why did we put 0.75 and not 6?
This one asks us for a cosine function. So for cosine, I'm looking for the maximum, not the rising midline. Any other questions? No? Okay. Last one. Yeah. All right, a wave pool. Who's been to a wave pool before as a child? Only 3 of you? 5 of you? Yeah, you have. All right.
Yeah, it's lucky gross though.
Yeah, it like starts a wave, and then like everybody in the wave pool just like goes over the wave. So you guys, you know how there's like that waiting period in between, like, so the water's like at a resting level, and then everyone's just like in the wave pool, like waiting for the waves to happen, and then like a wave starts. So this is the type of generator that I'm talking about, the generator that will actually like start that wave and push it out into the wave pool. Okay, so remember these good times? Let's just reflect back on our wave pool experiences. All right, our wave pool generator, which is essentially the machine that makes that wave that comes out in the wave pool, it moves back and forth 20 complete cycles every minute to produce waves measuring 1.2 meters from the top of the crest to the bottom of the trough. Model the displacement d in meters of the wave from the mean pool level as a function of time t. The water is 1 meter high at rest. Okay. And then it asks us to sketch a graph and model over 2 cycles. And then part C is a bit of an extension to this. So why don't we start with, we'll do our sketch again. Start with our sketch here.
Do you create these questions?
Sometimes, other times no.
Did you do this one?
No, I got this from somewhere.
Good. A lot of big game wave pool generator.
Okay, so what is y representing here?
Height.
Good. Height in meters versus time in seconds. Maybe I'll extend this a tiny bit here, just in case. Oops. And we are told that the resting, so if we're in the wave pool and we're waiting for the wave generator to start, the water is resting at a height of 1 meter. Now, usually wave pools, they kind of like go into like a bit of a deeper area, but we'll assume our wave pool is all 1 meter high. So 1 meter, actually Actually, that doesn't make sense. Oh, no, it does. Never mind. We're good. I thought my example didn't make sense. So 1 meter, that's the resting height. Now, if our wave pool starts and the wave must measure 1.2 from the top of the mountain to the bottom of the valley, basically, what's the distance from the midline to the top and the midline to the min? I heard a lot of numbers thrown out there. So the whole wave is 1.2 high? 0.6. So if I go up 0.6, which is half of 1.2, I'm up at 1.6. And if I go down 0.6 from there, I'm at 0.2. The distance from 1.6 to 0.2, oh no, sorry, 0.4 I meant. The distance from 1.6 to 0.4 is 1.2. That's what it's saying. From the minimum all the way up to the maximum, we're at 1.2.
Wait, where'd you get the maximum from?
So if my whole minimum to maximum is 1.2 units, it's actually telling me that the whole height of my graph is 1.2, right? The amplitude of that graph is the amount that we go up from the middle and down from the middle to get to the max and the min. That's half of the whole height of the graph. So the amplitude is actually half of the height from max to min.
Did they tell us the 0.4?
Yeah, I was just wondering.
No. They told us 1 and they told us 1.2. So I know
Oh,
that the whole graph is 1.2 units, so I need to figure out half of 1.2, because that's giving me my distance from max to min, 1.2. So I divide it by 2 and I find that if I go up 0.6, I'll reach the maximum from 1, and if I go down 0.6, I'll reach the minimum from 1. Okay, so your amplitude, remember, is half of the distance from your minimum all the way up to your maximum. So if I have the distance from the bottom of the trough to the top of the crest of the wave, I can find half of that to find the amplitude. So to find how much I need to go up from the resting height of the water and down. Okay, so we have to go up 0.6 and down 0.6 from that. Okay, if the water starts at resting height at a time of 0, the water height is at 1 meter. How long does one cycle take? If I do 20 cycles every minute, how long does one cycle take?
3 seconds.
Okay, so if I say B as far as period, if I do 60 seconds in a minute over 20 cycles, that gives me 3 seconds per cycle. Agreed? I can do 20 cycles every minute, so each cycle must take 3 seconds then. Okay, so if I'm graphing this over 2 cycles, I want to get up to 6 seconds here. So at 3 seconds, where am I? If I started at the midline and one cycle takes 3 seconds, what is the height of my water at 3 seconds? Pardon?
It's a full cycle then.
At the midline, yeah. So it's a full cycle. So it must have done inside here a full mountain and a full valley and got back to the midline. And also at 6 seconds, I'll be back at the water's resting height, which is the midline as well. So if I have to do a full mountain and a full valley here in order to complete a full cycle, where does this occur? Where does the next midline in that cycle occur?
1.5.
At 1.5, that's right.
Wait, do we know if it's like cosine or sine?
This one just says sketch a graph. Yeah, this one we could do either, so maybe we'll choose the better option once we have our graph done.
Well, wouldn't it be cosine if it starts, no.
Okay, and I also, sorry, I guess I didn't draw that super well, but maybe I'll just move down this tick here, put it right here. Okay, where does the max height occur then?
0.75.
0.75, that's right. And how about the minimum height? What's halfway between 1.5 and 3? 2.25. If you're not sure, add them together and divide by 2. That's how we find the center of two values, right? So 2.25 is the middle there. One question that you probably should be asking yourself is, how do I know it didn't go like this? Because that's also a full cycle. I'm assuming if the wave generator is creating a wave to start, that the wave is going to come out of the generator, right? So I was making a bit of a common sense assumption that the wave will start and then it will kind of go down from there as the generator gets turned on. That's a guess, right? Otherwise I would need more information. Okay, and then we have one more cycle. Where does the middle point between 3 and 6 occur? 4.5, good. And then we need the max point and the min point here.
That would be 3.75.
3.75 and
Then 5.25.
5.25, awesome. Okay, so that looks like a good graph. I will pencil that in as a solid line now. And here's our midline. We actually know the resting height of the water, so we have our midline right here. So I think we know that our C value is equal to 1. Okay, we already found our amplitude. That was the distance, half the distance from the max to the min. So we have A, we have C. If I know the period, can we find the K value?
Yeah.
How do we do that?
2 pi over the period.
What's the period? Oops, sorry. The period is 3 seconds, right? That's the length of a cycle. Sorry. So we will do 2 pi over 3. And that doesn't need to be reduced, so we'll just leave it. And this one actually doesn't give us an instruction as to whether we should use sine or cosine. Does anyone have an idea what we should use here? What makes the most sense? Why do you guys say sine, Jonathan?
Because the D is 0 if you use sine, because the rising midline is right at 0.
Yeah, so our rising midline is already on 0, 0, or 0, 1, I guess. But it's already on 0 as far as the D value shift. So if I use sine, my D value is actually 0. Can you use cosine for this? Absolutely. So your cosine function would be 0.75 to the right if you wanted to use cosine. But I think sine is a good option here because D will be 0. So let's just put this together here. What should we use? H at T, I guess.
Could you also write down the cosine?
Yeah, sure. So if you decided to use cosine, this is what your function would look like.
So why did we decide that D of sine is 0?
Because the rising midline right here is on 0 for x. 3 is technically another option, like 3 to the right. You could have used that as well. Okay, so that's parts A and B right there. Part C asks us, suppose the operator increases the speed of the wave generator to 30 complete cycles every minute. what changes would you expect to see in the waves, and how would you model your change? I'm going to ask you to talk to your partner about that for a couple seconds and see if you guys can decide how that would change if we change from 20 cycles a minute to 30 cycles a minute.
Thing would be together in more than a shorter amount of time.
The K value is just pi, and
All right, what are your thoughts? How would the amount of waves that you see in a minute change? Sam?
A lot more in a shorter amount of time.
So there would be more waves in that minute that you would see, so the waves would occur more often. What changes would we see in the actual model that we created here? Jonathan?
K value would change to pi.
The K value would change to pi. How did you get that?
Well, because we know that since a cycle is 30 seconds, we can do the calculation for B. So 60 over 30, which is just 2 seconds per cycle. Then we can plug that into K, that's the K value. The two twos cancel out, and you just get pi.
Okay. Okay, so the change that we would see in the amount of waves in that minute would be, we would see more waves per minute because we're completing more cycles. And then Jonathan said that if we have 30 cycles per minute, I have 60 seconds, and that gives me actually 30 cycles. So it takes 2 seconds for each cycle here. That is my period. So if I'm going to change the model that I created above, when I go to calculate the K value here, it's actually going to be 2 pi over 2 seconds. And I will actually just end up getting pi for K. So my h at t function would now change to pi times t in the brackets. That's it. Jonathan? Yes. Any questions on this one? We're okay? Also, just as a little aside note here, I changed minutes to seconds here intentionally because my question actually tells me that the function should be modeled with t as time in seconds. Otherwise, I would not have done that. If it said time in minutes, we would have calculated this differently. It would be 1 minute per 30 cycles, and my b value would be 1 over 30 here. So just make sure that you look for what unit of measurement the question is actually asking you about.